Now we are going to compute the self-inductance of a solenoid. There's not much shapes that we can actually compute the self-inductance, so that's the only example that we can solve in here. So as a result, I just want to say a few things about this. So there are these physical parameters in here. It's the length of the solenoid. There's this cross-sectional area, this also enters, so that's that area in here. And the total number of turns of wire also enters into the picture. So there's an assumption in here, of course, so we cannot compute the self-inductance of any coil. So somehow it has to be sufficiently long so that we can make this infinite solenoid assumption. And that assumption would be approximately valid, of course. So this is a necessity for actually doing this calculation. So let me just state what it is. So there is this length scale in here, and that gives the size of the cross section. So that length should be much smaller than the total length of the solenoid. Since the area is proportional to the square of that distance in here, you can also take it as the square root of area is much smaller than the length or something like that. But in any case, that's an essential condition. So if this is satisfied, then I can compute the magnetic field assuming that this solenoid is infinite. So as a result, my approximation would be valid. And that's essentially what we do. So how can we compute this? Well, we have already computed it, actually. We have solved this problem of two solenoids. One of them is inside the other one, but they had different cross-sectional areas and different lengths. So just take these as two identical solenoids, but different ones. It's essentially the same circuit, but you can, if you want, you can think of them as different so that you can compute the mutual inductance between these two circuits. So as a result, you're going to get the same answer. In any case, let's just do it with the second time with this approximation, with this point of view. I have just a single solenoid in here, so there's a wire in here that carries a current I, and this has n turns, so therefore the number of turns per unit length is n over L. And I know that there's a magnetic field inside, which is given in magnitude as mu0 times n times the current. So what about the flux? Flux is essentially this magnetic field multiplied with the area. But we have said that for this circuit, since there are n turns in here, I can think of each turn as a single loop. And I have essentially n loops in here. So as a result, I have to multiply this basic flux expression with the total number of turns to find the total flux of magnetic field that crosses this enclosed surface. Okay. So as a result, then we just write this thing down. So the magnetic field is mu0 Ni times the area. And for the number turn density, I just write down the total number of turns divided by the length. So as a result, this is mu0 n squared Ae divided by the length multiplied with the current. As we have said, the flux is equal to the self-inductance. L is the self-inductance multiplied with the current. We have said that the flux and the current have the same sign. So for a positive current, the flux would be positive. This is always the case, whatever the circuit is. So as a result, for this situation, therefore, the self-inductance is equal to mu0 times the number of turns squared multiplied with the area divided by the length. Right, so we are going to use this formula later when we are discussing the energy of the magnetic field. So in any case, for any kind of a circuit too, you can compute the flux like that. So for example, if I have a rectangular loop of wire like this, I can also compute the flux in there. So all I need to do is to compute the magnetic field inside. So we know that the magnetic field inside is pointing towards us, and outside it is pointing into the screen. So in any case, therefore you have to find the expression of the magnetic field inside, and then well, that's going to be a variable. It's going to depend on position, and then integrate this. So this will unfortunately be a double integral, because I have to multiply the magnetic field with the area element. So as a result, you just need to choose some kind of a small area in here and then do an integration. So as a result, this is a very complicated calculation. So you then need to show that this is equal to an expression that's proportional to I, and then read of the coefficient. That's one difficulty, however. There's another difficulty in here. We know that when you are very close to the wire, if your point is somewhere in here, let me use a different color for that purpose. So suppose that you are very close to the wire, so that distance is, let's just call it as R. In that case, the magnetic field, when you are very close to the wire is going to look like an infinite wire to you. So as a result, the magnetic field expression has this mu0 I divided by 2 pi r dependence. So in any case, it is proportional to the inverse of the distance to the wire. But if you integrate this thing, assuming that the wire has 0 thickness, if you integrate this thing, you are going to get infinity. So this integral would then give you an infinite result in such situation, assuming that the wire has 0 thickness. So this kind of tells you that this essentially tells you that the self-inductance of a wire, if it has 0 thickness, is infinite. So for real wires, therefore, somehow you have to cut this integration at some point. So you have to take the thickness of the wire into account. So as a result, from that perspective, the calculation of self-inductance of simple circuits like that, a rectangle, for example, is not as simple as it looks. So somehow, it's not just the size of the rectangle, but the wire thickness also enters as a parameter in there. But in any case, for these kind of circuits as well, or any kind of a circuit, any kind of an electric circuit, since this circuit somehow encloses some kind of a surface and there's a magnetic field that's crossing in here, there will always be an inductance in here because of that reason. So every circuit has an inductance, but usually this is very small so that we don't see their effects most of the time. So as a result, we neglect this, but that's one of the things that we should always keep in mind. That's basically we are making an approximation when we are neglecting the inductance.